Welcome to our mini lecture series on water isotopes and climate. My name is Axel Timmermann and I'm the director of the IBS Center for Climate Physics at Busan National University in South Korea. This lecture series provides additional background information for a high school science project called KWIN, which is short for the Korean Water Isotope Network. Here at the ICCP, at our center, we just call it KEVIN. The main goal of the project is to obtain measurements of water isotopes of rainfall across South Korea. This information will be useful for understanding the rainfall mechanisms in East Asia. The data will also help scientists from our center to reconstruct past climate changes from stalagmite samples in South Korea. For the schools who have already participated last year, we would like to thank you for your continued support to KWIN. In the following lectures, we will include some of the data you collected last year. Obtaining long data sets over many years is crucial for understanding the atmospheric processes over Korea. For the schools who are just joining the KWIN program, a warm welcome to you, and we appreciate your feedback at any stage during the project. The subject of our lecture series is water. We may think, water, this sounds boring. Chemical H2O. What can be there interesting about it? I will tell you a story about some secret information that is stored in water molecules. If we can read the secret information, we will learn a lot about the atmospheric circulation, rainfall processes, even about ice ages. The first lecture today will be about the story, or if you like, the history of water. Let's first relax and take a look at the water that surrounds us every day in our environment. Our center is in Busan, which is right at the ocean. The ocean is the biggest reservoir of water on our planet. The water is of course salty, and in some places it is also heavily polluted with chemicals and plastic. Let's look up at the sky. What do we see? We see clouds. What are clouds? Clouds are made of little water droplets and ice crystals. They develop when water vapor condenses in the cooler air and sticks together, sometimes enabled by little dust particles or other aerosols. When clouds cool too much, or when the cloud droplets become too big, it can start to rain. This rain then falls onto the land and oceans. On land, a part of it seeps into the soil. We can see this process in caves where the water is dripping from the ceiling. But we will come back to this later. The largest part of the continental rain eventually goes into the rivers, where it flows back into the ocean. Over the oceans, water can easily evaporate, generating water vapor, which can form new clouds. This closes the loop, or we call it the hydrological cycle. Where does the water on our planet Earth actually come from? This is an interesting question, an easy question to ask, but a difficult one to answer. Currently, the understanding is that much of the water on Earth came from collisions with asteroids in the early days of our planetary history. This conclusion is based on the fact that Earth's water and water on asteroids have the same hydrogen isotopic abundances. Comets and other processes can be ruled out as important contributors. So when I drink my cup of tea, I'm in fact drinking extraterrestrial water. Cheers. Water, H2O, has 2 hydrogen atoms and 1 oxygen atom. It looks a little bit like Mickey Mouse, with 1 face and 2 big ears. Normally, the hydrogen atoms consist of 1 proton, positively charged, and 1 electron, negatively charged. Standard oxygen has 8 protons, 8 neutrons, no charge, and 8 electrons. So in total, for water, we have 10 protons and 8 neutrons. Interestingly, the hydrogen atoms and the oxygen, they tend to share the electrons. This means that the hydrogen side of the water molecule is slightly more positively charged because the electrons belong to the hydrogen prefer to hang out near the oxygen. In contrast, the oxygen side is getting a slightly higher negative charge. This charge asymmetry inside the water molecule is called polarity. If we include a few more water molecules, it becomes clear that they try to arrange themselves in a way that 1 positively charged hydrogen side, called a delta plus, gets attracted to 1 negatively charged oxygen side, called delta minus, of another molecule. This creates a force which we call hydrogen bond. Under low temperatures, water forms ice, which has many hydrogen bonds. They contribute to the crystalline structure of ice. The liquid form of H2O has fewer bonds, and water vapor, gaseous water, has no hydrogen bonds, because the thermal collisions of molecules in a gas break up these weak electric forces. If we want to understand the physical properties of water, we need to understand how it responds to changes in temperature and pressure. You probably all heard that water boils at lower temperatures when the pressure is low. Boiling describes the transition from liquid water to gaseous water vapor. One of the key diagrams that characterizes the physical properties of a substance is called the phase diagram. On the right side, we see the phase diagram for water. To understand this diagram, we will start at normal pressure, 1 atmosphere, and room temperature. Let's move around in this diagram. If we heat up the water at room temperature, it will boil at 100 degrees Celsius, transition to water vapor. If we decrease the temperature, it will freeze at 0 degrees Celsius. If we decrease the pressure at room temperature, we can also cause boiling at very low pressure of about 1/10 of an atmosphere. There is even a point at a temperature of about 0.01 Celsius and a pressure of 0.006 atmospheres, at which all 3 states, liquid, solid, and vapor, can coexist. This point is called the triple point. As I mentioned already, water molecules carry a little secret. It turns out that not every water molecule is the same. There are differences. In fact, there are 18 different types of water molecules. Chemically, they're almost the same. But in terms of their physical properties, they are different. What causes this difference? The difference comes from the fact that we can add electrically neutral protons to the nucleus of an atom. This makes the atom definitely heavier, but the electric charge is the same. We call atoms of the same chemical element with different number of neutrons in the core isotopes. For water, the most prevalent one is the one for which oxygen has 8 neutrons in the nucleus and 8 protons. The total number of nuclei is 16. That is why we call it H2-16O. But we can add 1 or 2 more neutrons to the oxygen, making it H2-17O or H2-18O. These heavy isotopes are not very abundant, like 0.04% or 0.2% respectively. But they are the key part of our K-WIN project. Changes in their abundance in rainfall samples will tell us a lot about the climate system, but more about this later. We can also add neutrons to the hydrogen. One neutron more makes hydrogen deuterium, and 2 neutrons more create the radioactive tritium. Let's take a step back here from the atomic world. From now on, we know that water in our environment is composed of 99.7% light water, H216O, and 0.3% isotopically heavier water. This is not much. Does heavier water H218O taste differently? Does it look differently? The answer is no. So why should we care about it? In order to understand why isotopes carry a secret message, we need to first introduce a new notation. If we take a water sample, say an ice cube from a glacier, we can measure how many heavier water molecules are inside relative to the lighter ones. More specifically, how many H218Os versus H216Os. We learned that roughly this ratio, which we abbreviate as R, is close to 0.2% or 2 per mil. But it can vary. The variations are so small that it makes sense to compare the ratio of one sample, for example glacier ice, with that of another sample, for example ocean water. Let's call the ratio of ocean water our standard. In nature, we find that glacier ice from Greenland, for instance, has a slightly lower 18 to 16O abundance ratio as compared to seawater. If we divide the abundance ratio of ice by that of ocean water, we obtain a number of approximately 0.972. To avoid using small numbers, we subtract 1 and multiply the result with 1000. This means the ice sample has what we then call a delta 18O ratio of -28. Standard ocean water, according to this definition, has a value, delta 18O value of 0, and normal rainfall over Korea, for example, would have a value of roughly -7. If a water sample has a negative delta 18O, we call it depleted. If it has a positive value, we call it enriched, always with respect to standard ocean water or more well-defined other standards. Now the question of course arises. What controls these magic numbers? And that is where physics and climate come into play. There are several processes how differences in delta 18O can emerge. Let's first focus on the so-called equilibrium fractionation process. Imagine a closed bottle filled with water. The water contains a certain number of H216O and a certain number of H218O molecules. Inside the bottle, we will at a given temperature quickly obtain an equilibrium between the number of water molecules in the vapor and liquid form. The ratio of vapor and liquid concentration will be called K. Now it turns out that this number is greater for lighter water H216O than for H218O. This makes sense as less energy is needed for the lighter water molecules to leave the liquid as compared to the heavier ones from H218O. Now coming back to our definition of the isotope ratio R, and given that K18 is smaller than K16, we can then show that the ratio R in the liquid is higher than in the vapor. Heavier H218O preferentially stays in the liquid phase. Now let's imagine a different system which is open to the environment. the gas phase of vapor is not in exact equilibrium with the liquid phase anymore. We call the occurring fractionation between 18 and 16 H2O kinetic or disequilibrium fractionation. An open pot of boiling water is a good example. We have lots of water molecules with high kinetic energy. It turns out, like before, with the equilibrium fractionation, that in order to kick a heavier H218O out of the boiling water, we need more energy because it is heavier, because it has 2 neutrons more than its sibling H216O. So over time, the remaining liquid water will accumulate more of the heavier water molecules. It is enriched in delta 18O, which means the ratio of heavier over light increases over time, whereas the water vapor will carry more of the lighter ones. This is a typical result for open systems, such as a lake in summertime which evaporates water. From now on, we will know that the evaporated water vapor will preferably have reduced delta 18O ratios as compared to the lake water. But then, what happens to the evaporated waters? Where will they go, and what will happen to the isotope ratios on the way? In order to understand this, we move back to the phase diagram of water. We need to understand what happens to the isotopic ratios when water vapor condensates. When in the phase diagram we move from the right water vapor to the left water. This happens in clouds, when small droplets form, or when droplets in a cloud become so big that rain will fall. When water condensates, some part of the thermal kinetic energy of the initial gas gets released. This energy is called heat of condensation. As we can expect, it is equal to the amount of heat required for vaporization. This means that a water droplet has a lower energy state compared to the gas. As we have already seen before, this means that heavier water molecules preferably aggregate there. The lighter ones stay in the water vapor. This is exactly the opposite process as for the vaporization discussed before. Rainwater will be less depleted in 18O as compared to the water vapor it originated from. The more condensation, rainout occurs, the more depleted the water vapor will get in heavier delta 18O. Let's picture this in our daily life. Whenever we freeze water, or melt water, boil water, or when water vapor condensates, like on my glasses when I enter from cold outside into a warm and humid room, we will know from now on that there is an important process taking place which is hidden to our eyes, but which we can measure in our lab. Water fractionates with every phase transition. With this knowledge in hand, we can now make a cool little calculation. About 20,000 years ago, our planet experienced a massive ice age. Big ice sheets lay over North America and Europe. We know from measurements that the ocean was enriched in heavy 18O by about 1 per mil, 0.1%. Later on, I will explain how we can measure this. Does this number tell us anything about how much ice was on land? Also, if we take water from the ocean and put it on land, also the sea level will drop globally. Let's try to find out by how much. One of the key assumptions is that if we look at the combined system ocean plus ice, Today and 20,000 years ago, the total number of water molecules, including H218O and H216O, remained the same. We just have a redistribution of 16 and 18O between the compartments. One other important piece of information is that an ice sheet typically has a delta 18O value of -35 per mil or -3.5%. Under present-day conditions, we have N molecules in the ocean with an isotopic ratio R of 0. Under glacial conditions, we have N minus delta N molecules of water in the ocean with an isotopic ratio of R minus delta R of 1 per mil. Furthermore, we have delta N molecules of water in the ice with an isotopic value of -35 per mil. From this, we can write down the total mass balance as R times N equals R minus delta R times N minus delta N plus the isotopic ratio of ice times delta N. Now, if we assume that the number of molecules is proportional to sea level, we can then calculate the glacial sea level change as 0 times 4,320 meters, present day, equals 1 times 4,320 meters minus delta sea level, minus 35 times delta sea level. From this we obtain 4,320 meters divided by 36 is delta sea level, or delta sea level is 120 meters. Glacial sea level was 120 meters lower than present day. This means that China and Korea used to be connected. There was a land bridge which got flooded as the ice sheets melted and sea level rose. This little example shows us how we can use water isotopes to infer something about global sea level. Pretty cool, isn't it? We are starting to get a sense now about the power of water isotopes, to learn something about the different compartments of water in our climate system. We have water in the oceans, in lakes, in rivers, in clouds, in the air as water vapor, and as liquid in the rain and cloud droplets. Water is in the soils. We see it dripping from the stalactites in caves. Water is in icebergs, ice sheets, glaciers, permafrost on land and swamps. Everywhere it will have a specific water isotope signature, like a fingerprint, which helps us to identify the processes that brought the water to these places. How we extract climate information from delta 18O of water in different environments will be the subject of the second lecture. I hope you enjoyed this little introduction into the secret information of water and that you will join me for the second lecture.